Hello guys, this is Saddam Cap. Welcome to my channel. As you can understand from my previous videos, my doing of quantum mechanics is completely unconventional from your regular classroom. Because what I follow is how historically you can understand how the quantum mechanics, the theoretical model, has been evolved as time goes. Well, in this video, I am going to talk about how differential operator, or let's say how you can write Schrodinger equation in a matrix form, because previously or so many times I have told you that there are two ways of doing quantum mechanics. One is calculus method and another is matrix method. But you haven't seen so far that how actually differential operator can be written in a matrix form. And in this video, I will first start with Dirac notation and introduce you the matrix form of Schrodinger equation, and then we will interpret this whole thing in terms of Hilbert space, that how all the basic postulates is arrived in quantum mechanics, that wave function has to obey this so-called normalization, square integrable, finite value, and psi and its first derivative has to be constant. In Dirac notation, I can write like psi of x can be written as this notation, like psi, okay, or psi of x. This is called Kate notation. And similarly, I have been introduced psi star x. Psi star is means conjugate of psi, conjugate of wave function, and this is also called dual, and this can be written as this one psi, and this is called brass. Okay, so there are two specific kind of notation, the cat notation and brass notation. Cat is represented by this one and brass is represented by this one. In matrix formalism, this psi or this one simply called column matrix. Column matrix means like this one, this one, this one, this one, all the elements goes like here. And this guy or psi star x, which is star means like dagger, okay, it's nothing but psi dagger of x, and dagger means transpose and conjugate. So this column vector will become row vector, okay, or column matrix become row matrix. Well, I have already told you these things actually represent your matrix as well as these eigenvectors, okay. Psi is state of the system, or we call it eigenbasis or basis or eigenvectors. So anything I can use in the middle of whole video, so never confuse with the terms, okay. Now, as you have seen, I have also defined the scalar product. So if, for example, we have two vectors or wave functions like psi and phi, and I have to take like a scalar product, like in vectors, what happens to two vectors? A dot b can be defined as a b cos theta, and this scalar product will always be a scalar, means it will give you some number. So to define a scalar product, one used to do in Dirac notation like here, psi and phi, the sandwich between the brass and cats, which is like in the previous thing, I can write psi and phi, and in algebraic form, I can write here minus infinity to infinity. Now this guy goes for psi star, and this matrix goes for this one, and simply dx. You have already seen in the derivation of particle in a box, particle in an infinite box, how we have done this psi, okay. We have written here infinity infinity psi star psi dx, and this goes for normalization. So if two vectors or two eigenvectors are normalized, then I can write here psi phi is equal to 1 or psi is equal to 1, okay. Now if two vectors are orthogonal, then psi phi will goes to 0, okay. This says the orthogonality condition. Now, as we have discussed in earlier, that psi can be superposed of like some constant and phi n, or suppose psi n, Well, so I can write here simply psi n psi m del mn, and or del nm. If m is equal to n, it will give 1 for m is equal to n, and 0 if m is not equal to n. This also defines that if the two states are same, it will be normalized, and if two wave function corresponds to different states, then it will always vanish. Means two states corresponds to different, two wave function corresponds to different states is always orthogonal. Okay, so this is the simplest thing, and one can also say that suppose psi, let's see the property, let's analyze the property of this Dirac notations. Like psi phi, this is the inner product, and if I do dagger, then what I can do, it will just simply change its position like phi and psi. The same thing goes like suppose A and B are two matrices, and if you do the sum conjugate, so what happens, like B star and A star, okay, and they will remain same because this is the scalar product, and you do this transpose, you do this conjugate, and it doesn't change its value. Okay, but in so many examples you will get that, so many examples like in mathematical example, suppose you will say that psi can be like 2 3 plus I or 4, and suppose phi is given to you like 3 4 minus I or 2, then if you do this inner product, then this guy psi phi is not equal to phi psi. Why? There is some issue goes there. Okay, so never mind. Now what I'm going to write again, like suppose you have this A of psi and B of phi, and you are taking the dagger. A is some kind of a complex number, it may be real, it may be complex. So what I can do is here, you are seeing simply doing the dagger, means complex conjugate and transposing, so it will give like A star, and this column matrix become row matrix, so it will become like here, and again B star, and it will be same like this. Now if you have some kind of a constant A and psi, you write, so you can write here simply like this way, and similarly you can write here A psi, well psi here. Okay, so these are the things which you have to remember, that how you can actually deal with this Dirac notation while writing this thing. And again there is a one inequality you have, that suppose you are sandwiching or inner product two wave functions, and you are just taking its norm, so this is less than or equal to psi psi and phi phi. These are the type of identity, or these are the type of equation which is so much important while you were giving some kind of a competitive exams, because so many things which will be asked in this kind of stuffs. Now one thing, that suppose my ket vector is psi, and if it is given like A, I, B and C, and another ket vector given like phi, and which is nothing but B plus IC and suppose D. Now one can ask that what is the product, like, well, psi times phi. Okay, now psi is my row vector, so it will become A I B psi with conjugate or dagger. Let's say conjugate, because I have already made it to this row vector, means transposing it and make the conjugate, and again it's simply column vector B plus IC and then D. So this will goes like here, A star minus I, B star and C star, and this one simply like this. So it is the same matrix multiplication, so you don't have to worry about it. Now row goes to column, and it will be simple as matrix product. Like here it will go A square, because A is trying to A star, then minus IB will, so it will my minus I, B again square, then it will multiply with this thing plus B star C, and again this will multiply with this thing C star D. Okay, So this is kind of a general idea. Now A corresponds to some kind of a number, B corresponds to some kind of a number, and so on. So this is the way you have to treat how you can do the inner product of two matrices. Okay, and as you have seen earlier, what is the definition of this inner product in an integral form, like we have done in my particle in a box. Okay, how these operators act on cats. Suppose like I have some kind of operator psi is acting on psi will always give some kind of eigenvalue, and psi eigenvalue corresponds to number. Now all the operators in quantum mechanics has to be Hermitian in such a way that A Dirac must be A, because if it's not there, then this eigenvalue will not be real. So to get the eigenvalue real, you need to have this Hermitian operator. And I have discussed whole things in my previous video, like lecture 3. So you can see there. You can see my lecture 3. Well, if I am doing this kind of thing, well, do the diagram. So what happens? So if I do this, if I am breaking down, so what I can write here, simply psi A Dirac. Okay. Now what does this mean? It means that A operate on psi, because A Dirac, so A Dirac will always acting on this guy. So A acting on this one. Now if A is acting on this one, because it's bra, so A becomes A star. So here it will become A star psi. Okay, so this whole thing has the same meaning, so it's so much important. Now suppose two matrices, suppose phi m A, and again I operate on this thing. So if I do this thing, now A psi gives me A psi. Well, A will come out because A is a scalar quantity. We'll have phi m. Now A will acting always this one. I cannot make it act in this one. Well, because A is my Hermitian matrix, so I can also act on this guy also. Okay, so it will not have any problem, but in general it will act on this thing, and we are having this product here. So A phi m psi. Similarly, you have the momentum operator, like P acting on psi will give me, suppose, any eigenvalue, let's say P and psi. Now we know what is the momentum operator, like h bar over di d by dx. Psi is a function of x. Now P psi, P is a scalar quantity, some number, so I can write here d psi, okay, d psi by psi integral, like pi over h bar dx integral. So it will become log of psi. So I can write here psi is e to the power I p over h bar x. Okay, so this is the simple thing, that any wave propagating with some momentum, it represents the plane wave. So we can always write psi for the momentum operator like this. Now if you have any operator like identity operator means there is this kind of a matrix which gives all the elements like in diagonal. Okay, so if I am operating this kind of operator, it's identity matrix, and it will simply gives you the eigenvalue like 1. Another thing here, I can say you a1 phi 1 plus a2 phi 2 psi. So how you can do this kind of thing? Well, a1 will become star phi 1 psi plus a2 star phi 2 psi. If I do this thing like psi a1 phi 1 plus a2 phi 2, so the whole thing is a1 psi phi 1 plus a2 psi phi 2. These are the algebra which is so much important, because you are in the phase of learning quantum mechanics, and if you don't have habituate with this kind of algebra or with this kind of notations, then it will become so much problem, because we are going to solve harmonic oscillator, we are going to solve this kind of angular momentum problems. So there the operator algebra, these kind of Dirac algebra which he has introduced, is going to so much in use. So be careful with these kind of things, because it's a very new thing which you have never encountered with like what is the operator and how these wave function are actually acting this thing, and these things are actually gives you nothing but a inner product. So the whole calculus has been boiled down to simply this kind of a notation, cats and bras notation. Well, we have find out in particular in a box that there is a kind of expectation value of operator, like we have done this expectation value of momentum or we have position. So how can we do this thing? So what is the meaning of this thing? So suppose we have to find expectation value of some kind of operator. So this definition goes like here, like psi, well, A goes psi. So this is the inner product, okay, like I have already told you, and psi into psi. In quantum mechanics, the wave function must be normalized. Therefore, this psi inner product will always equal to 1, and hence I can write A is equal to psi A psi, and in waveform it is nothing but minus infinity to infinity psi star A psi dx. Now you can operate this thing here or you can operate this thing here, because I have already told you A Dagger is nothing but A. So you don't have any problem to operate that. You cannot say that okay, I will just operate here or I will not just operate here. You can operate anywhere. It's completely nothing to do with all these things, okay? So you're cool with this thing. That's why the quantum mechanics makes your life simple, that you don't have to worry about anything. Now well, if you have a momentum operator like P, so P will go into like h over I del by del x. So if you do this dagger, so what will happen? Minus h by I del by del x. Now I have already told you this del by del x is nothing but again minus h bar by I minus of del by del x. So it will remain h by I del by del x. So therefore P dagger is always be P. Now your question become clear that okay, this also goes true with momentum operator, and you know x dagger is simply x dagger and it has the eigenvalue of x. So you can do all this sandwich thing, it doesn't care, but it also goes with momentum. You don't have to worry about these things. Well, now one more thing is that psi, if I take this A dagger, okay, now phi. So what else you can do? I can write, before I have already told you, like this guy will be operated here, A of psi and phi, and it will give A star psi and phi, okay. Other thing I can do here is this one, I can write like phi A psi with star goes here, because I know this will just interchange the place, and now A will operate here. So I will get A phi and psi all to the power star. Now A becomes A star and it will interchange psi phi. So this is the same as this one. So I can say here like psi A dagger phi will be same as phi A psi to the power star. So you don't have to confuse with this kind of things that it is something else or something else. Both the things are the same thing. Now if you have having some kind of operator like e to the power IA or e to the power A operator, and you are applying this some kind of a basis here, so what is this? This A will act on this one and it will give the eigenvalue here only, okay. Don't confuse with this thing, don't write A here. It will always operate this thing and will give you the eigenvalue, and you just write this eigenvector here. Now if I am saying that, suppose as we have had definition, it's a very important thing what I am going to write, going to do here. Less it's given, and one more thing is given, that there are two operators A B is equal to B A, okay. As I have already told you, this generally doesn't happen, but in a very particular case, like if two operators A B is equal to B A, means that you change the order and nothing happens, everything remains same, then what will happen? So Suppose I am applying this guy like here. What would be the eigenvalue of this thing? Well, what I can do here, because a b can be interchanged, like ba psi, and a psi will give you a. Now a will just disappear and b goes like here. So what is tell you that a is acting on b psi. Now b of psi will become the eigenvector of a and give you this eigenvector, okay, this eigenvalue a with the eigenvector b psi. So this tells me, this is a very important thing, this tells me that b also, this psi, the eigenvector also become this. Now the b will again have the common eigenvector of a, because I know in quantum mechanics, if you do any measurement like a acting on psi, I am doing the measurement. Now system will be some kind of a psi dash, okay, in some different states, because the measurement change disturbs the system and the system will occupy in new state. Well, what does it say? That you acting a this one and it has new state. So what is say now ab, now these operator can be interchanged, therefore I can say ba change. So if a changes this one to new with eigenvalue like here psi dash, so this eigenstate will be same for this another operator b, because they are independent of order. Okay, so this says that though both a and b will have this common eigenstates. Okay, so this I can go further and dig deeper and again describe here that a hat b hat minus b hat a hat is equal to 0, and we say that this guy, these the two operators, they commute each other. So if two operators commute each other, then these both operators will share the common eigenbasis or common eigenvector. Means if I operate a in psi, it will make the system in different state, but if I operate b on the same state, like a psi gives you psi bar, so if I would have operate b first, now it will also end up in the same state. So this is the mean that if two operators commuted, means a hat b hat is equal to ba, the operators are independent of their order, so they will share the same state. The eigenvalue may be different, but the state would have been same. So you apply the system a first and then b, and then b, it will be same as b applies on first and then a. Okay, they would have different eigenvalue, but they will share the common ground state. Okay, I will dig deeper on commutator, that what does it mean, that what happens, how to do the algebra of commutation, like a b is equal to 0 or may not be equal to 0. What will happen if they are not equal to 0? Then they will not have any common eigen space or eigenvectors. Okay, so two operators can have the same eigenstate only if they commute with each other or they are independent of order. So it's the most important fact. So as we have seen here, like a operates on this whole is the eigenvector of this operator and gives you the a eigenvalue and this one. Now before I have already seen this was the eigenvalue because psi was the eigenvector of a. Now here become that b of psi becomes the eigenvector of this operator. So I can safely say that psi also will be the eigenvector of b. So therefore I can write here b psi is simply some kind of eigenvalue with eigenvector psi. So both operator will have the same eigenbasis. This thing is so much important because in later, as our course progress, we would have encountered that suppose there are two different kind of operators, and we have to find what would happen to states when we are applying. So there we must know what would be the commutation of that two operator and how those eigenbases will change when we will apply. Now one more thing I could suggest, I will say you that x and p is not independent of order, means they are not equal if I am doing this. Hence if I am applying to this guy, it will produce this one, and if I am applying the same state, this one, so it may be different things. So they don't share the common eigenvector, hence their commutation is not equal to 0. One measurement changes the system in another state, and other measurement changes the system in another state. So that's why it is called that in quantum mechanics, measurements changes the state. So you have to find all this operator which actually commutes so that your life becomes so much easy, and you would have very much understanding of the system, because these operator corresponds to this operator, the wave function or states of the system will share the same wave function. Well, we will understand it deeper in later video, like in my next video. And now I will now I am doing something different, and I will tell you how I can actually formulate this matrix mechanism for quantum mechanics. Now one more thing, how one can say this, you have seen that AB is not equal to BA, and this is the simple property of also matrix, that if you multiplying two matrices, the order, if you change the order, they may not commute. Okay, so you will see in matrix formulation that the commutation relation actually arises very independently and so much interestingly, and these brackets are called Lie brackets. Okay, and all the algebra goes for this Lie brackets. Well, let's see the matrix formulation of Schrodinger equation. So first of all, I have this Schrodinger equation like H operate on psi is going to give me some eigenvalue of E. Now H can be written as ps square by 2m plus v of x, and p square simply goes like d2 over dx square plus v of x. Well, if I am writing this in terms of in this fashion, like d2 by dx square psi plus like 2m by h bar square of vx psi x is equal to 2m by h bar square like e psi of x. Just multiply 2 by m h square. Now for particle in a box, we had 0 to L, and we have told you that the inside the particle in a box our interaction is 0, so there is no any potential which is interacting with particle. So my job is very much simple. So d2 psi by dx square is equal to, well, minus 2m over h square e of psi x. Let's write the whole quantity in k square term, and we can have d2 psi by dx square plus k square psi x is equal to 0. So this is my wave equation. Okay, this is my wave equation or Schrodinger wave equation. Okay, and now we have to solve it analytically. We have to solve with the additional condition, because I know to solve this kind of equation we need to have boundary conditions. Without boundary conditions we are nothing. We cannot actually see anything about the system. So boundary condition is necessary in quantum mechanics. Whenever you solve the Schrodinger equation, first of all you have to figure out what's the boundary condition, and you know that at the boundary the wave function must goes to 0. So if you are solving some kind of a hydrogen problem, that this is the nucleus and there is some electron is going here, so boundary condition says that as, suppose this is my r, as r goes to 0, the wave function must goes to 0, and goes for infinity, then psi at infinity, r goes to infinity, it must be 0. So there are two wave functions, that at far from the nucleus the wave function must be 0, because the probability of getting the electron far from the nucleus is completely 0. There cannot be, you cannot find there, and inside the nucleus there will be no any, or r is equal to 0, there is no any probability to finding the electron inside the nucleus, or let's say at r is equal to 0, there cannot be any finite value of finding the electron inside the nucleus. So these are kind of a boundary conditions, and there are so many more. So you have to understand the boundary condition in order to do quantum mechanics. If you are not understanding the boundary condition, then there is no way you can do quantum mechanics.